After studying this module, you shall be able to know the applications of the selection rules of IR Raman spectroscopy. Learn how to predict the geometry of the molecule. Identify activities of the vibrational modes for various geometries. Find some examples for practice. Distinguish between various geometry of AB3 type molecules. We have seen so far how an IR and Raman spectra are complicated due to the various types of side bands, overtone, combination or difference band, hot bonds, Fermi resonances. If one is able to analyze the IR spectrum correctly and properly, then by knowing the fundamental vibrational modes and Raman bands, it is possible to predict the geometry of the molecule. For obtaining tau vibrations, we can use internal coordinates, bond angles and bond vectors as the basis for representation. Now, to explain this point, the fundamental modes and geometry of the molecule, and I will take now first the example of FeCO5, ferric pentachloride. Now, based on the VSI part theory, we can assign two geometry to this molecule as given in. First is trigonal bipyramidal molecule. It is like this, that is trigonal base. Here is a CO, this is also CO, this is also CO, this is also CO, this is also CO. It is a TBP molecule. This is one geometry. Another possible geometry is, it is like this, 4 CO on the base and this is like this. So, I am having two geometry possible for this molecule TBP, which has a D3S symmetry, and then square pyramidal geometry which has C4 symmetry. Now, the various symmetry elements present in these molecules, symmetry operation of these molecules, we have already discussed in our beginning modules on symmetry operation and symmetry elements on the molecule. Now, I have to decide which structure is correct for iron pentachloride and how this group theory helps in this. Now, let us go for the finding the tau reducible and then reduce the tau reducible by taking internal coordinates. Here I will take 5 FeCO bond as the internal coordinates. I will not consider the angles. Let me just take stretching frequencies only. Bond vectors as the basis for representation, and we can get reducible representation, and this can be reduced further. Let us first take the square pyramidal geometry. C4V, using 5 CO bond vectors, we can get the result, and we take the C4V symmetry character table. Now, in this C4V character table, unshifted vector, that is the last but one row, unshifted vector 5, 1, 1, 3, 1, that is the under operation E, 5, all the 5 vectors are not shifted. Then under C4Z, only the axial bond vector is not shifted. Under C2, coinciding with C4, again 1 is not shifted. Under sigma V, 3 bond vectors are not shifted, and under sigma our D, only 1 is shifted. Sigma D, where the 3 bond vectors are not shifted, it means it contains 1 axial FeCO and 2 your horizontal FeCO bonds. And now the character for tau CO is 51131, and this can be reduced to by taking the character table for C4V as 2A1 plus B1 plus E mode. After doing this, let us check the IR and Raman activities of these bonds, and these are given in table as 2A1 mode, B1 plus E, and IR activity yes, no, yes. That is 2A1 is IR active and E is also IR active and B1 is not. Raman activity 2A1 yes, B1 is no, E is yes. Modes which are IR active, 3 IR active and 4 Raman active FeCOH. That is, if I consider C4V symmetry, there should be 3 IR active modes and 4 Raman active modes, though some of these may be coinciding. Now let us take trigonal bipyramid geometry, D3H geometry. We can obtain the vibrational mode again by using 5 CO bond vectors and character table of D3H point group. Unshifted vector, that is FeCO. For E it is 5, 2C3 it is 2, that is both the axial FeCO. 3C2 it is 1, sigma H it is 3, 2S3 is 0, 3 sigma V is 3. Chi contributed and the tau CO is 5, 2, 1, 3, 0, 3. Using standard reduction formula, tau vibration can be reduced to irreducible representation. That is, tau CO is 2A1 dash plus A2 double dash plus E dash. Let us now check the IR and Raman activity of these modes. 2A1 dash IR active or not? No. Raman active? Yes. A2 dash IR active? Yes. Raman active? No. E dash mode IR active? Yes, and it is Raman active is yes. That is modes which are active, 2 IR active modes and 3 Raman, and the actual IR Raman spectrum, IR plus Raman spectrum is shown, and you find over here it contains 2 IR bands and 3 Raman bands. It means the geometry of the molecule in question is TBP, trigonal bipyramid. If it would have been square pyramidal, we would have got more IR bands and more Raman bands, that is 3 IR and 4 Raman bands, but we are getting only 2 IR and 3 Raman. So this spectrum corresponds to trigonal bipyramid geometry. Next, let us take the example of xenon tetrafluoride. Based on VSEPR theory, we can assign the geometry to this molecule as shown in figure. That is, it can be a square planar, all these 4 fluorines are there into this, or it can be a tetrahedron like this. That is, this fluorine, fluorine, fluorine and fluorine. So we can have these 2 types, square planar or tetrahedral. And based upon now this, by making use of the application of the molecular symmetry, I can predict which structure is correct. Using internal coordinate method and using only 4 xenon fluoride bonds here as the basis for representation, we can obtain the reducible representation, and then reducible representation can be reduced to irreducible representation, and the result for the reduction for various geometry can be compared. Let us first take tetrahedral geometry. Using 3n vectors as the basis, using character table of TD point group, we get the tau vibration as tau 3n minus tau t minus tau tr is equal to tau vibration is equal to A1 plus E plus T1 plus 2 T2. Now, and this tau 3n, which is obtained as we have discussed in earlier, it is 15, 0, -1 and 3, and even on reduction we can get the result as A1 plus E plus T1 plus 2T2. And let us check the activities of these A1 modes. A1 is Raman active and polarized, E is Raman active and depolarized, 2T2 bands are IR and Raman active. Thus, we get 2 IR bands and 4 Raman bands, and 1 band is polarized. If it is a TD geometry, if it is a tetrahedral geometry for xenon tetrafluoride, according to our theoretical prediction, it should get 2 IR bands, 4 Raman bands, and one of which should be polarized. 2 IR and 1 Raman bands are common. This is important point. Now, if the molecule belongs to D4H point group, that is, if it is a square planar molecule, using 3n vector as basis and taking the help of the character table of D4H point group, we get tau vibrations as A1G plus B1G plus B2G plus A2U plus B2U plus 2EU. The activities of these bands are given as over here. A1G is Raman active and polarized, A2U IR active, B1G is Raman active depolarized, B2U IR only, B2G Raman only depolarized, 2EU is IR only. We get 4 Raman bands. These 3 Raman bands and 1 Raman band is polarized. We get 4 IR and 3 Raman bands, and 1 Raman band is polarized. The given spectral frequencies are, that is what we find. IR frequencies we are getting 586, 291, 161. Raman we are getting 554, 524, 218. Do you find any of the frequencies are common? IR frequencies and Raman frequencies are not common. In these frequencies, none of the IR or Raman frequencies are common. Mutual exclusion principle holds good. That is, none of the frequency is common. So, definitely this molecule xenon tetrafluoride has center of inversion, and so this is important point. It has center of inversion, and due to this we can immediately predict if I am getting IR frequencies not common with the Raman frequencies, so this molecule has center of inversion. Now, let us take the next example. Let us take AB3 molecule. Based on VS-EPR theory, we can assign the following geometry to this molecule as shown in figure. That is, it can have a pyramidal geometry over here. This is A, B, B and B. This is a pyramidal geometry. It can have planar geometry A, B, 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 or it can have this type of geometry, that is A, B, B and B. So, in these 3 geometries, that is pyramidal geometry, the molecule belongs to C3V point group. In the planar geometry, the molecule belongs to D3H point group, and in this type of molecule, T-shaped molecule, the symmetry or the point group for this molecule is C2V. So, we will consider now this AB3 molecule, and just by noting this we can find out. Thus, we find AB3 molecules based on VS-EPR theory can be assigned a C3V type of molecule, a D3H type of molecule, a C2V type of molecule. Using group theoretical arguments and selection rules for IR, Raman spectroscopy, and by making use of 3 coordinates AB bonds in all of these, we can develop the reducible representation, and then it can be reduced to irreducible representation, and then IR activities can be checked. And the results for the IR activity of Ab3 molecule in C3V point group is summarized as A1 IR yes, Raman yes polarized, E in IR yes, Raman yes, and then A1 is again yes, yes polarized, E yes, yes polarized. Thus, for Ab3 pyramidal, all four modes will be IR and Raman active, and two Raman bonds are polarized. In D3H point group molecules, A1 dash, IR no, Raman yes, E dash yes, yes, E dash yes, yes, A2 dash yes, no. That is 3 IR and 3 Raman bands are obtained for D3H symmetry. Only two bands are common in IR and Raman and one band is polarized. Now for AB3 in C2B point group, A1 mode yes, IR Raman yes, A1 yes, yes, A1 yes, yes, B1 yes, yes, B2 yes, yes, B2 yes, yes. We have 6 IR and 6 Raman bands which are active in both. Thus, by knowing the vibrational modes and their activities, it is possible to ascertain the geometry of the molecule. Sometimes, when we have same number of vibrational and Raman bands for different geometries, then it is polarized or depolarized nature of the Raman band can help a lot. Totally symmetrical A1 or A1 dash modes are Raman polarized always. All these bands for all geometries are summarized in table. For C3V, IR modes are 4, that is 2A1 plus 2E. For Raman modes, again there are 4, 2A1 plus 2E. And two Raman bonds are polarized. For C2V, 6 IR modes, 3A1 plus B1 plus 2B2, and 6 3A1 plus B1 plus 2B2, and 3 are polarized. D3H, 3 IR active A2 double dash plus 2E dash, and similarly Raman bands 3 A1 dash plus 2E dash and 1 A1 dash is polarized. So, we have this table, and if we have the data with us, we can immediately predict the geometry of the molecule. Let us take PCl3 molecule. Using the data as given in table, we can predict the geometry of this molecule. Experimental vibrational spectral data for the molecule is 192 centimeter inverse, 260 centimeter inverse, 485 centimeter inverse, 510 centimeter inverse IR active modes, and Raman spectrum 190 centimeter inverse, 261 centimeter inverse, 486 centimeter inverse, 515 centimeter inverse. Raman active modes are, and two of these are Raman polarized. On comparison, data in table clearly points out towards C3V symmetry for PC3L molecule. For BF3, the spectral data is 480 centimeter inverse, 690 centimeter inverse, 1450 centimeter inverse are 3 IR active modes, and 480 centimeter inverse, 688 centimeter inverse, 1454 centimeter inverse are 3 Raman active modes, and one more is polarized. This data fits very well for D3H symmetry for BF3 molecule. For CLF3 molecule shows 6 IR band 320, 365, 435, 525, 700 centimeter inverse, and 6 Raman active modes, that is 322, 365, 435, 525 and etc. like this. Now, on comparing the data in table, this spectral data fits very well with C2V geometry for CLF3 molecule, that is T symmetry, T shape, and which is well known. Now, in this module, we have learned so far how the selection rules of IR and Raman spectroscopy can be applied and can be used. We can predict the geometry of the molecule using normal modes of vibration, provided we are able to analyze the IR spectra or Raman spectra properly. That is, if we avoid all other side bands. Activities of the vibrational modes for various geometries have been examined and used for ascertaining the geometry of the molecule. Some more examples have been discussed, that is by taking AB3 molecules, 3 possible geometries C3V, D3H, C2V. Journal has been taken, and then by taking the example of POCl3, BF3 and another example of C2V group, that is ClF3, which has the T shape, all these data have been compared and their geometries can be easily predicted, and the result is very well within the experimental error. So, just by making use of this IR spectroscopy, now in all these modules so far we have discussed in IR Raman spectroscopy, we have basically learned how to find the activities of IR modes. What are the bases? That is, we can make use of the bond vectors, angle deformation as the mode of vibrations, and also we have learned how to assign the spectral frequencies to these various modes of vibrations. Also we have learned in all these IR models or Raman models, that is how their spectra are complicated due to the presence of hot band, overtones, combination bands, difference band, etc. And in the last module we have learned to make use of the various applications to predict the shape of the various molecules.